Lecture 10. In this lecture, the second lecture on transverse waves, we will look at what happens when the transverse waves from the previous lecture interact with their boundary. As a lead into what happens at the boundary for those transverse waves we defined in the previous lecture, we're going to first use the separation of variables technique for the wave equation and see what we get. It's a technique which we use to hunt for solutions of a specific form. Specifically, we suppose that our wave equation in one dimension, we suppose that it has a solution of this form. We don't know if it does. We're going to see, perhaps it does. We're going to do that by substituting it into the differential equation, in which case we just get this. And then I can divide by x of x and t of t on both sides to get this, which is something that must hold for all x and t. But look, the expression on the left is only in terms of x, and the expression on the right is only in terms of t. Yet those two have to equal for all values of x and t. So that's only going to be possible when both sides are equal to the same constant. So let's suppose that constant is, we write it as minus sigma, just to keep things simpler, as you'll see in a little while, where sigma is greater than 0. So in other words, something like minus 7 or minus pi or whatever. Then those two expressions equal to minus sigma. And then multiplying out, I can then write it in this form. So the first one, for example, if I take this equal to minus sigma, I just multiply by x on both sides and I get the minus sigma x, and then I add plus sigma x on both sides and I get this. And then I write sigma just as the square of the square root of sigma. Okay, so nothing funny. And of course, there's something similar for t, except there's a v term as well. Okay, now these two differential equations we immediately recognize from chapter 2. We know their general solutions. We played a lot with them. So there they are. This is old news. That's the general solution of those two differential equations, where c, d, and alpha and beta are just some constants. Hence the solution, in this case, remember we started off by supposing that there is a solution of the form x times t. And then we got to this point, which means that the solution in this case is then xt for that x and t, so that expression. And then yet again, using the addition formula for cosine that we've done employed so many times by now, and this I will leave to you to go and work out the details. You can write it in this form. So you can either try and see if you can write it yourself in this way, or simpler is just to use that expression and see if you can get the one above it, where the green and the blue are the two angles you use in the cosine addition formula. Okay, so we've yet again we've had to rely on those addition formulas in the trig functions, and that we can simply write in this form, where I set k equal to sigma x and omega equal to v squared sigma. And look carefully at what we have there. That is two transverse waves traveling in opposite directions. This one is traveling to the, this one is traveling towards the left. Remember, you should be able to tell from the previous lecture, and this one is traveling towards the right. So we see that a very general kind of solution to the differential to the wave equation is this case. We've got two waves traveling in opposite direction, and then their superposition, their sum, is a solution of the differential of the wave equation. Now we're going to look at where this occurs, or where this can happen. And now we get to reflection of waves at the boundary as a possible origin of waves traveling in opposite directions and then superimposing. Specifically, we're going to consider what happens when we've got two ropes that are tied at x equal to 0, and we've got a wave traveling from the left, and then we want to know what happens when that wave reaches x equal to 0. So this amounts to a transverse wave traveling in a medium, and the medium suddenly changes. So in principle, at least, what we're going to conclude from this in the mathematics and physics we're going to do now should not restrict us to situations where we physically have a string or a rope or something that changes thickness at some point. Just in the same way that the spring dashpot mass systems from the previous chapter the mathematics and analysis we did not physically restrict us to systems where we had actual springs and dashpots and shock absorbers and masses. Okay, but anyway, we suppose that we've got a tension T in the rope that's constant. And then because the two linear densities are different, we've got two different velocities necessarily. V1 would therefore be equal to the square root of T over mu1 and V2 the square root of T over mu2. And we're always going to suppose that there is a wave incident on the rope from the left. In other words, it's traveling in a positive x direction, and then we want to figure out if we want to see if we can figure out what then happens. So let's be a little bit more precise. So there we have our incident wave, which you should be able to tell is traveling towards the right. Something gets reflected, we don't know what, so let's add it. Something gets reflected, so that wave is traveling towards the left. And something gets transmitted. We don't know what it is, but we're going to see if we can find out something. Now, to determine what happens at the boundary, we're going to define two values and see if we can derive expressions for them. The first is the amplitude reflection coefficient, AR divided by AI. And here we're going to allow the values, these A values to be negative. Only AI we're going to assume we're going to take as positive necessarily. That will be the starting point. So this one will always be positive. But these two we won't fix like that. We'll see what they are relative to AI. But anyway, we'll get to that. The other one that we'll be interested in is the amplitude transmission coefficient. So AT divided by AI. We're going to see if we can find some useful expressions for them, and then if we can interpret those expressions. And before we do that, we're going to have to identify two boundary conditions, because at this stage we do not have enough information to get something useful for R and for T. The first condition will be the continuity of displacements, and this simply amounts to the fact that what's going on the left, remember on the left is the incident and the reflected wave, so yi and yr, these two functions are only for the left side, only left. Mathematically, necessarily, they will exist this side as well, but we ignore that. Our model for the actual string and what it does will be on the left side yi plus yr, and on the right side yt. Therefore, we necessarily have to have the situation in which they meet at x equal to 0. If they do not meet at x equal to 0, then that means that at 0 there is a vertical displacement, a vertical gap between yi and yr and yt. That can't happen because the two are fixed. You can't have that this rope goes like that and then a thick rope starts here, of course. So they are connected at x equal to 0 is essentially what this means. In particular, when t is 0, it just means that ai plus ar must be equal to at. The second one is that the continuity of that transverse force Fy. And it amounts to simply saying that we can't have a sharp angle here at x equal to 0. Because if we do, then that's going to mean an infinite force on a very small section of the rope. So we're just basically saying that what's going on here as it transitions from the one rope to the other rope, it doesn't do that at a mathematically sharp angle. It does that in a continuous fashion, which is not unreasonable at all. So it's just making a continuous smooth, it is a continuous slope at x equal to 0. So that's all that means. Okay, so exercise 2, we've got to derive those two expressions for the respectively reflection and transmission amplitude coefficient. And in exercise 3, prove that relationship between T and R. All right, so what we're going to do is we're going to prove that relationship, that characterization of R, and then do exercise 3, and then get that expression for T from exercise 3. That would be the simplest way to go about it. All right, so let's start. Number 3. Okay, so how are we going to derive that expression? It's a very simple exercise. We just effectively write down what those conditions are. Here's the first one. Amplitude of the incident plus that AR of the reflected must be equal to AT of the transmitted. Okay, well, that's the first condition, 1. And the second one is that effectively the string must be smooth at x equal to 0, so yi plus yr. Okay, now this is just normal partial derivative, so just differentiation with respect to x, where everything else is treated as a constant. So for those expressions that we gave, it is going to be cosine omega t minus x over v1 plus omega over v1 reflected cosine omega t minus x over v1. Okay, and that should be equal at x equal to 0 for all t to this partial derivative minus omega over v2 at cosine omega t minus x over v2. Okay, and this must be at x equal to 0 for all t. So at x equal to 0 for all t, these two must be the same. And what does this mean? All right, so at x equal to 0, what happens to these terms? Well, that just falls away. And all that I'm left with when at x equal to 0 is a cosine omega t term, cosine omega t term, and a cosine omega t term. And that has to be equal for all t. So in particular, for when t is 0 and when and x is 0, what are we left with? We're just left with that term and that term and that term. So that term plus that term must be equal to that term, where omega is the same across all of them, so I can just divide that out. That means that what must therefore be true is minus 1 over v1 a incident plus 1 over v1 a reflected must be equal to minus 1 over v2 a transmitted. So I can just simplify this a little bit, multiply with v1 on both sides, so then with minus v1 on both sides, so then I get a incident minus reflected must be equal to v1 over v2, and then this transmitted. All right, so that is a second condition that I have. And now to get r, I'm just going to equate these two. All right, so okay, so what do we have? According to the first one, how shall we go about this? Let's multiply, because we've got this term, let's multiply the entire first condition with v1 over v2. So I then have that, if I multiply this entire thing with v1 over v2, I have that v1 over v2 times ai plus ar must be equal to v1 over v2 at. So that's just the first condition. And by the second condition, this must be equal to ai minus ar. Okay, so now I'm just going to equate the two. So the at falls away. So let's see, what do I have then? Then I've got ai and ar term on one side and an ai and an ar term on the other side. So let's just group all of the terms. So let's put the ars on the left, because we're going to divide by ai to get the reflection coefficient. So let's keep the ai's to the right. So let's put ar to the left. So what is its coefficients? Well, it is v1 over v2, and when I bring that ar over, then it means it's plus 1 equal to, okay, and what do I have this side? ai. Here I've got 1, and when I bring that one over, it is minus v1 over v2. Okay, so now let's write that as a single fraction. So that is ar times v1 plus v2 over v2 equal to ai, and then this is v2 minus v1 over v2. Okay, so I can multiply v2 on both sides. All right, so then what shall we do? Now we're going to divide by ai. So that is just the reflection coefficient. That's what I get when I divide by ai, and then that is equal to, what do we have here? I divide that, then I've got, if I take this and I divide it by that, then I get v2 minus v1 over v1 plus v2, which is exactly the expression that we were after. But we also know that, v1 from a wave equation, then the speed in that string is the tension divided by the linear density in that string, and the same for V2. The tension over the linear density in that part of the string. So this I can simplify then, or not simplify, just write in a different way. So V2 is therefore equal to, okay, I'm running out of space here. So this is going to be T divided by mu2 minus tension divided by, what's that V1? So mu1 over, let's write V2 first here. So T divided by mu2 plus T divided by mu1. Okay, and then I can divide by 1 over the square root of T on both sides. So then I'm going to get, when I do that, I'm going to get a 1 over square root of mu2 minus 1 over square root of mu1 over 1 over the square root of mu2 plus 1 over the square root of mu1. Okay, and if we simplify this, okay, let's see, let's continue here at let's continue here. Okay, so let's say we're now going to continue here. See how nicely we indicate it. If you want to continue problems, also make it clear where you are continuing, so that we don't have to search for the answers. Okay, so how can we simplify this? Well, oh, I see. Okay, so here's got 1 over something, 1 minus 1 over something. So I'm just going to write that as equals to, this will become square root of mu1, yes, minus square root of mu2 over the square root of mu1, mu2. So I wrote the top just as one fraction. That's what I did there. And then I'll do the same below. And then here it will become square root of mu1 plus square root of mu2 over square root of mu1, mu2. And then these two cancel. And what we're left with is a square root of mu1 minus the square root of mu2 over square root of mu1 plus square root of mu2. Sure, all right. Long process, but nothing complicated. It was just long, not difficult. I just got my two conditions. I had took my first one directly, and I wrote my second one in a slightly different form. Combined them, and immediately got the first expression that was asked, and then simplified it a little bit by replacing v1 with its expression, and then got it in this form. So there I have it exactly. Now, to get the expression for t, oh, this was actually exercise 2 that I did, not 3. So this is 2. Now for 3, we want to prove that t is 1 plus r. So all that I'm going to do there is I'm going to see that ai, that we already know that ai plus ar is equal to at. So if I divide everywhere by ai, what do I get? Then I get 1 plus the reflection coefficient is equal to the transmission coefficient, simply by dividing on both sides by ai incident. Okay, and now from that you can easily find that t is therefore equal to 1 plus r. So 1 plus, okay, I'm just going to do the one side, the other side you find the same way. So 2v2 over, no, that's what I want to show. Let's see, let's start over. T is equal to 1 plus, what's that reflection coefficient? V2 minus V1 over V2 plus V1. Good. So I just write that as V2 plus V1 over V2 plus V1 minus, plus V2 minus V1 over V2 plus V1. That is then 2V2 over V2 plus V1. Okay, so to get that expression is trivial given the condition, and then I can just use the previous result to easily get the expression for the transmission amplitude coefficient. Right, now that we've got an expression for R, let's see if we can come to certain conclusions. Let's suppose that the incident wave is meeting a thicker rope, or just one that has greater linear density. So mu2 is greater than mu1. Then this top term is negative and R is therefore negative. And remember what R is. It is R divided by AI. If that's negative, it means that AR and AI have got different signs. It means that those two waves are 180 degrees out of phase. But because the one wave is traveling in the one direction and the other one in the other direction, it might be a little bit tricky to interpret that correctly. So let's look at an example. Here, I've got the incident example where I've got an incident wave and a reflected wave and the transmitted wave and the whole total story. So, and here's the boundary at 0. So here, this part is the incident plus reflected, incident moving towards the right, reflected to the left, and here green is the transmitted part moving towards the right. In this case, the reflected and the incident have the same phase. And the way that you can see that is that blue and red are here at the boundary, both positive at the same time, negative, they become 0 at the same time and become positive at the same time. So here positive, positive, and when it goes below the line, they do so at the same time, and both are negative at the same time. So this is in phase. This is not 180 degrees out of phase. This is in phase. It's almost as if the incident wave is just entering a portal and immediately coming out here. If it enters here at the bottom, it exits here at the bottom. If it enters here at the top, it exits here at the top. It's a little bit squeezed in it clearly, but it doesn't change direction vertically. So this is an example of in phase. So this is not 180 degrees out of phase. This is in phase. Out of phase is here. See, where the exact opposite happens. When the incident is positive, then the reflected is negative and vice versa. So the top one is still entering a portal to get to the bottom one, but the bottom portal is kind of flipped upside down. So this is an example of where red and blue are 180 degrees out of phase. Okay, so now let's look at the actual example. And here I apologize, this is a extremely rudimentary simulation of a string that is simply modeled purely with Newton's second law, viewing the string as a bunch of sections. At each time step, it simply calculates the vertical resultant force, given that the string is under constant tension, and then just calculates what it should do. So it's not using the wave equation, it's not using any sine or cosine function, it's purely Newton 2. So here I'm going to send away from the left, and then we're going to see what happens when it encounters a thicker rope towards the right. And it should be 180 degrees out of phase. So the reflecting wave should go below the line. And you see there it does it, 180 degrees out of phase. And the wave keeps going. Okay, so that nicely illustrates at least 180 degrees out of phase. Okay, now the other way around. Now u2 is less than mu1, mu2 is less than mu1, so now our R is positive. So now A subscript R and A subscript I have got the same sign. So the reflected phase, the reflected and incident wave have the same phase. So when the pulse now reaches the point where it reaches the boundary, then the reflected wave should not go below the line. It should stay on top. So let's see if we see that. So the reflected wave back should not invert. It should stay on top. Now let's see if that happens. And exactly, yes it does. Purely Newton 2, not wave equation or anything funny. And now finally, let's look at two cases simultaneously. When mu2 is equal to 0, what would that mean? That means the linear density of the medium into which the incident wave hits is 0. So it's hitting nothing, which is a little bit difficult to imagine with a rope like this, because there needs to be something there to get your tension. But I mean, we can at least temporarily ignore that. So that's the one case. What happens for this kind of string if it's somehow still under tension but it hits nothing? Perhaps it just hits another string that's extremely thin compared to the string that contains the incident wave. That's the first case. So in this case, this string is only fixed towards the left and not towards the right. Okay, so then the second case is when mu2 becomes infinite. So that would mean that the linear density of what the incident wave hits is infinite. So that would be like it's hitting a stationary object. It's hitting a point that can't be moved. So it's like a string is attached to the wall there. So you can see in those two cases, look at the definition of R and or not the definition of R, the expression for R that we derived. In those two cases, R work out to 1 and -1 respectively. So in the case where it hits nothing, there should be no phase change, so the wave should not invert as when it reflects. But when it hits a solid wall, it should invert so that you can get to 180-degree phase change. So let's see if we see that. Okay, so there it is. Now it is fixed there at 0. Now the wave goes and it's going to hit, well, nothing or effectively nothing. And that should not mean a phase change, so the wave should come back on top as well. And it does, there it is. So there we see a reflection with no phase change. And now let's see, when it comes back, it should do 180-degree phase change. So that wave should dip below and invert. Let's see if we see that. And purely Newton 2, very pleasant to see. And there it goes. Okay, so even though it's a very rudimentary model of a string, it at least shows what happens in real life. Okay, and that is it for the second lecture on chapter 5.